Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to continue our discussion on the averages of random variables. In particular, we're going to look at the means and variances of some common random variable types. Before I get into the main material for this video lecture, I want to step back a bit and do an example that I probably should have done in the previous video. So, this is an example that relates to the material I discussed in the previous video. Alright, in particular, I made a claim something like this. I said that if I take a random variable, or create a random variable y by taking a random variable x and subtracting the mean of x, I claimed that y is a zero mean random variable. Let's prove that. We'll look at it a couple different ways. First of all, remember the mean value of y, which can be designated mu sub y, equals the mean value of x minus the mean of x. And this is the expected value of a function of x, and that can be found by integrating from minus infinity to plus infinity of g of x times the probability density function of x dx. And that then can be written as integral from minus infinity to plus infinity of x minus u of x times the probability density function. And expanding this out, I get integral from minus infinity to infinity of x times its probability density function minus a constant which always comes outside of my integral sign. Okay, well, now let's notice that the area under any probability density function is exactly 1. And this is the expected value of x. So we can continue, we can say that this is the expected value of x minus mu x. Expected value of x can be also written as mu x minus mu x and 0. Good for us. So we have confirmed rigorously that if I form any random variable y by taking a random variable x and subtracting its mean, y is indeed a new random variable with a 0 mean. Alright, I said I'd do this two different ways. So let's use some of our shorthand notation and use some of the properties of expectation to get exactly the same result, maybe a little bit quicker. The expected value of y is the expected value of x minus mu x. And applying the properties of expectation, this is the expected value of x minus the expected value of mu x. Expected value of x is just mu x, its mean value. The expected value of a constant is always a constant. And once again, we get 0, just like we expected. So, by using our rigorous definition of the mean of a function of random variable, we get that the mean value is 0. when I take a random variable and subtract off its mean. And we also get the same result when I use my shorthand notation, applying the properties of expectation. So, hope that might help clarify any confusion you might have from some of my comments that I made in the previous video lecture. So, let's get on to the main material for this particular lecture. And let's look at the means and variances of several common random variable types. We're going to begin with the Gaussian random variable. We're going to begin with the Gaussian random variable. Remember, the Gaussian random variable has a probability density function that looks like this. Okay, looks something like that. If we sketch this out, this should start being a fairly familiar figure for you. This is X. This is my PDF. All right. As with all proper probability density functions, the total area is unity. All right. This Gaussian probability density function is symmetric about the value m, and due to the symmetry of this probability density function about m, I know the total area is 1, so the probability that random variable x takes on a value greater than m, this red hatched area, is a half. The total area is 1. The red hatched area is a half, and that's because that's due to the symmetry of the problem. Likewise, the probability of random variable x being less than little m is half. The area of the the green hatched area is also a half. So you'll remember from the previous discussions that the mean value of a random variable is the value above which and below which we're 50% likely for my random variable to take on a particular value. So it's safe to say that my little m is the mean value or expected value of x if x is a Gaussian random variable. So we've kind of talked it through here. Let's actually prove that. Let's calculate the mean of a Gaussian random variable and prove rigorously that the mean value is actually little m. All right. We're still talking about a Gaussian random variable. Let's find the mean value. That's how we do it. And let's plug in my PDF. I get an integral from minus infinity to plus infinity x times e to minus x minus m quantity squared over 2 sigma squared over sigma square root of 2 pi dx. Let's make a change of variables. Let's let u equal x minus m and du equals dx. Make my change of variables and I get an integral from minus infinity to infinity of u plus m e to minus u squared over 2 sigma squared sigma square root of 2 pi du. Break that down one more time and I get an integral from minus infinity to infinity of u e to the minus u squared over 2 sigma squared over sigma square root of 2 pi du plus m times integral from minus infinity to plus infinity of e to minus u squared over 2 squared sigma square root of 2 pi du. A lot of writing. Okay. Now, notice that the integrand here is a proper Gaussian probability density function simply with zero mean. All right? The probability density function inside of the integral on the far right-hand side is a zero mean Gaussian. For that reason, it's a proper probability density function, and that integral is exactly equal to 1. All right? Next thing, notice that in my integrand to the right, u, this function here, u, is an odd function, and that my zero mean Gaussian is an even function. That's an even function. What do I mean by that? Hopefully you've seen this before. An even function, f sub even, evaluated at x naught equals f sub even evaluated at minus x naught. This is an even function. All right? Cosine, for example, a cosine function is an even function. A zero mean Gaussian function is an even function. An odd function is characterized by this. F sub odd evaluated at x naught is negative f sub odd evaluated at minus x naught. That's an odd function. That's characteristic of an odd function. The sine function, sin of x function, is odd. A straight line that goes through the origin is an odd function. So here, u is a straight line function, linear function that goes through the origin. It's an odd function. Here I have a zero mean Gaussian function that's even. It's symmetric about 0. And you'll recall, I hope, from some calculus discussion somewhere, if I have an integral over all possible values of an odd function times an even function, my result is exactly 0. All right, I'm spending some time on this because from time to time through the rest of the semester, we're going to see integrals where we have products of odd functions times even functions. Instead of doing all the math, we can just say, well, integral of an odd function times an even function is exactly 0, and move on. So, proceeding, the first integral, because it's an integral of a product of an odd and even function, that's exactly 0, plus m times 1, and that's just m. So on the previous page, we sort of reasoned out that the mean value of a Gaussian random variable was m, but we proved it now from first principles. Okay? All right. What about the variance of a Gaussian random variable? Variance of a Gaussian random variable. Well, my variance looks like this. It's my second central moment. Variance is my second central moment. that's how I would calculate my second central moment. My function of x is x minus mu of x squared. This is my function right here. I find the mean of a function of a random variable by doing this. All right. Find the mean of a function of a random variable by integrating over all possible values the product of the function times the probability density function. My function in this particular case is x minus mu of x quantity squared. Let's let u equal x minus the mean and du equal dx. This then simplifies to integral from minus infinity to infinity of u squared, notice now that's an even function, times e to the minus u squared over 2 sigma squared sigma square root of 2 pi du. And I have to admit that that's a challenging integral to solve by hand. It involves completing the square and doing some other mathematical gymnastics. I'm going to let you do that on your own. So let's just say ... do several more steps, and you will find after doing the appropriate mathematical gymnastics that the result is sigma squared. All right? The standard deviation, the variance for a Gaussian probability density function is just that sigma squared parameter. Remember, the probability density function for Gaussian random variable x is 1 over sigma square root of 2 pi e to the minus x minus mu of x quantity squared divided by 2 sigma squared. Really, no kidding. Sigma squared there is my variance. That parameter in the probability density function is indeed the variance. That's why we use that notation all along. And if I take the square root of the variance, I just get sigma. Sigma is square root of the variance or my standard deviation. Okay? We've been using sigmas in my Gaussian probability density functions from the start. Well, indeed, sigma squared for the Gaussian probability density function is the variance, and sigma without the square is the standard deviation. Okay, I'm not going to take that any further. Just a lot of math that's not particularly very helpful. All right, let's look at the uniform random variable. We looked at the uniform random variable in the previous video just a bit. Let's remind ourselves of the results. This is what my uniform random variable looks like. Area, of course, is 1 in all cases. And previously we found that the mean value of a uniform random variable is just b plus a over 2. It's not very surprising looking at the probability density function sketch. And moreover, in the previous video, we found that the second moment, or normalized power, for a uniform random variable looks something like this. A squared minus, a squared plus the product of AB plus b squared over 3. That wasn't particularly obvious, but we did it in the previous video. All right, let's find the variance for my uniform random variable. And I'm going to use this handy relationship. The variance of x equals the second moment minus the square of the first moment. This is going to be a squared plus b squared over 3 plus ab over 3 minus a squared plus b squared over 4 minus ab over 2. All right. And this is 1/12 times 4a squared plus 4b squared minus 3 a squared minus 3b squared minus ab over 6. I'm skipping some steps here. I'm going to let you work out the details a little bit later on. This is 1/12 a squared plus b squared minus 2ab over 12. And my final result after all of this is 1/12 a minus b squared. You check my math. Okay? All right. So my variance for a uniform random variable is 1/12 a minus b squared. It's not a very good 2, is it? A minus b squared. And my standard deviation is just the square root of that. It's going to be 1 over square root of 12 a minus b. I guess probably I need to switch that around, b minus a. It's going to be a positive value. Okay? So that's it. We now have the mean. We have the mean squared, variance, and standard deviation for the uniform random variable. All right. If I was to sketch in up here, sigma represents the mean spread of values about the mean value. Remember, that's always what standard deviation is about. All right. Let's look at our next common random variable. Let's look at the exponential random variable. Exponential random variable. Exponential random variable has a probability density function that looks like this. And sketched out looks like this. Okay, that's what the exponential random variable looks like. Now, to calculate the mean squared values, I had to look up in my integral tables to find the following result. Integral from 0 to infinity of x raised to the nth power e to the minus ax dx equals n factorial divided by a raised to the n plus 1 power. Again, I looked this up in the back of an old calculus book somewhere, so I'll just say that I found this in integral tables. Okay? Look that up in an integral table somewhere. Forgotten where exactly. So let's calculate the mean value. The mean value of x is going to be integral from 0 to infinity. Alpha can come out front. X e to the minus alpha x dx. And using my integral table relationship, be alpha times 1 over alpha squared. That's just 1 over alpha. That's the mean value of a Gaussian random variable. The mean squared value is, the alpha can come out front, integral from 0 to infinity, x squared e to the minus alpha x dx. Using my relationship I found in my integral table, I get an alpha times 2 over alpha cubed, and that's just 2 over alpha squared. And then I can find my variance. I'm always going to use my handy shortcut relationship for finding variance if I can. Need to capitalize that to make that my random variable. This is going to be 2 over alpha squared minus 1 over alpha quantity squared. Simplify that, and I just get 1 over alpha squared. Or, taking the square root of that, I can find the standard deviation. Turns out for the exponential random variable that the standard deviation equals the mean value. All right? The mean value is 1 over alpha, and the standard deviation, which is the spread, the average spread of values about the mean value, that's also 1 over alpha. We could come up here, and that'll be about 1 over alpha. So this is my mean value. The standard deviation is 1 over alpha. The mean spread of values about the mean value for the exponential random variable is, in both cases, 1 over alpha. Right. What about a Rayleigh probability density function, or a Rayleigh random variable? Rayleigh random variable. Rayleigh random variable has a probability density function that looks like this. And this, sketched out, looks like this. Starts up, peaks up, and trails off. All right, that point is 0, and the peak is A. But as we're going to find, A is not the mean. That's just where the peak value lies. All right. Well, I also had to use integral tables for this. Let me write down the integral, integral table relationships that I found. The first relationship that I found that I needed is this. integral from 0 to infinity of x raised to the 2n plus 1 power times e to the minus ax squared dx equals n factorial divided by 2 times a to the n plus 1 power. Let me write that a little bit better. N factorial divided by 2 times a to the n plus 1 power. And this is valid for a greater than 0. Okay? Second relationship that I needed was integral from 0 to infinity of x raised to the 2n power times e to the minus ax squared equals 1 times 3 times 5 times all the way out to 2n minus 1 divided by 2 to the n plus 1 power times a raised to the nth power times square root of pi over a. That's a lot to digest, I know. I apologize. I'm not going to make you remember. I'm not going to make you memorize that kind of stuff. I'm giving you the tools to check my math. Okay? So those are the two relationships from integral tables that I need to find the mean and mean squared value for my Rayleigh random variable. So let's go ahead and do the math. The expected value, the mean value of a Rayleigh random variable is going to be 1 over a squared integral from from 0 to plus infinity. The Rayleigh random variable starts at 0. 0 to plus infinity x squared e to the minus x squared over 2a squared dx. Using my tables, I get a mess, which will simplify 4 1 over 2a squared All right. I really hope that you'll take the time to check my math. If you find any errors, please do let me know. Anyway, the mean value of a Rayleigh random variable is, it simplifies to something quite simple. It's just a times the square root of pi over 2. It's a little bit bigger than a. If we go back over here, the mean value is a little bit bigger than a. It's a times the square root of pi over 2. All right? It's 50% likely. It's 50% likely that my random variable x will take on a value greater than the mean value. So this red hatched area is 50%. And likewise, my green hatched area down here, that's the probability that my random variable takes on a value less than the mean. That's equal to, the area equals a half. Okay? A there is just where the peak of the probability density function occurs. The mean value is actually a little bit larger than where the peak lies. All right, back to our story. Let's find the mean squared value also known as the normalized power or RMS squared value. This is 1 over a squared, integral from 0 to infinity, x cubed e to the minus x squared over 2a squared dx. Using my integral table relationships, I get 1 over a squared times 1 over 2 times 1 over 2a squared quantity squared. That simplifies out to 2a squared. All right. So we can summarize over here on the right-hand side a little bit. The mean value for our Rayleigh random variable is a times the square root of pi over 2. The mean squared value is just 2a squared. And then we can find the variance. That's just going to be 2a squared minus a squared pi over 2. And that's a squared times 2 minus pi over 2. And that turns out to be, I'm just going to write down an approximate relationship for this. It's going to be a squared times 0.4292. Okay? Over here on the right-hand side, to summarize, my standard deviation can be written as a times the square root of 2 minus pi over 2, or my variance can be written as a squared times 2 minus pi over 2. All right? All right. One last common random variable that we'll encounter from time to time. Let's look at a delta distributed random variable. Delta distributed random variable. Once again, I refer you back to the probability density function for the random variable equal to the sum of spots up when I toss 2 fair 6-sided dice. My probability density function has this form. It's a sum of weighted delta functions. In this case, we'll let little piece of I equal the probability that random variable x equals x sub I, and the summation from I equals 1 to n of little piece of I equals 1, 100%. It's 100% likely to take on some value. And there are, of course, n values of my random variable x. All right? So, let's find the mean value. Actually, let's do it this way. Let's find the nth moment. Let's find the expectation of random variable x raised to the nth power. We'll do this all at once. This is the integral from minus infinity to plus infinity of x to the n times my probability density function. And this equals integral from minus infinity to plus infinity of x raised to the nth power times my summation probability density function. Alright, and this can be written as, I can interchange my summation and my integral. Alright, and then this equals summation from I equals 1 to n x sub I to the nth power times p sub n. Here I've used what's known as the sifting property. Hopefully you're familiar with that. Let me write it down here. The integral of f of x times delta of x minus x naught dx is just f evaluated at x naught. That's the sifting property of a delta function. And that is what I've applied to get my last result. Okay? All right. So, let's move to the next page. Let's remind ourselves that we found on the previous page that the expected value of random variable x raised to the nth power for a delta distributed random variable is the summation from I equals 1 to n x sub I raised to the nth power times p sub I. All right. Very simply then, the expected value of x, the first moment, little n equals 1, that's just summation I equals 1 to n x sub I raised to the first power times the probability that random variable x takes on value x sub I. So remind ourselves, little p sub I equals the probability that random variable x equals x sub I. And likewise, my second moment, or my RMS value squared, or normalized power, equals pretty straightforward. All right, and then my variance, which is just my mean squared minus the square of the mean. Very simply, that is summation from I equals 1 to n of x sub I squared times p sub I minus the square of the quantity there. Pretty straightforward. All right. So from time to time we will examine additional random variable types, and as necessary we will calculate their means, mean squared values, variances, and standard deviations. But that's all for today. And as usual, if you have any questions, please contact me at your earliest convenience, and I'll do all I can to clear up any misconceptions, errors, and answer all questions you might have. That's all for today. Have a nice day. Bye-bye.